Good afternoon, guys. So today we'll be discussing a couple of questions on kinetic theory of gases. This is going to be one of the most important topic for JEE main and Neet as well. So we'll start with question number one. Here it is given that Cp and Cv are the specific heat at constant pressure and constant volume. So it is given that is the Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume respectively, and it is observed that Cp minus Cv is equal to A for hydrogen gas. Okay, this is for hydrogen, and Cp minus Cv is equal to B for nitrogen. Okay, now the correct relation between A and B is, so we know using Mayer's formula, the relation between Cp minus Cv is equal to R over M, where R is the gas constant and M is the molar mass. Okay, we know the molar mass of hydrogen. Molar mass of hydrogen is 2, whereas molar mass of nitrogen is 28. Okay, now simply whatever is given to us is for hydrogen, the Cp minus Cv is A. This implies that A is equal to R by 2 and Cp minus Cv for nitrogen is B. So we can easily write that Cp minus Cv, which is B here, will be equal to R by 28. Okay, so let's put the value of R here. R is equal to 2A. We'll put this value here and we'll be getting B is equal to 2A over 28. So this will give us A is equal to 14B. Okay. Now out of these given options, A is the right option. Okay. A is the right option. Now let's move to, to the next slide. Uh, let's move to the question number 2. N moles of a diatomic gas in a cylinder are at temperature T. Okay. So there are total N moles present of it, and the gas type is diatomic here, and these moles are present at temperature T. Heat is applied to the cylinder such that the temperature remains constant. Okay, this is good that the temperature remains constant, but we are actually adding heat to the process or to the system. But N moles of the diatomic gas gets converted into monoatomic gas. Okay. So out of the given capital N moles, they actually got converted from diatomic to monoatomic gas. Okay. What is the change in the total kinetic energy of the gas? Okay. So let's first try to understand what actually this question is telling us. We have a cylinder, okay, where there are n moles of diatomic gas are present. Diatomic gas, okay. Now what we did, we actually added heat to it, okay, but the temperature remains constant. So T is constant, okay. This means this heat actually was used to break the diatomic molecules into monoatomic. Okay, so we can easily write that heat was used to convert diatomic molecules, or sorry, diatomic moles or moles into monoatomic moles. Okay, and that we know that there are n of them, actually they got converted. So due to this process, n moles of diatomic converted into monoatomic gas. Okay. This means the new monatomic gas molecules are 2n. Okay. So now we can write that the final composition of the gas is such that in this cylinder we have we have n minus n moles of diatomic gas, and there are 2n moles of monatomic. Temperature is T here, and same the temperature is T here. Okay. This means, and also because the volume is not changed, because the cylinder is still same, and both the gases after converting from diatomic to monatomic and before the complete gas, when it was diatomic, all these gases were in same volume. Okay, so volume is also same, so we can say because volume is constant, therefore work done by the gas or on the gas is zero, which is PdV, because volume is constant, so dV is zero. Okay, so simply the whole heat actually was used to change the kinetic energy of the gas, and that's what we need to calculate. So initial energy, kinetic energy, what we can write here is the degree of freedom. Okay, because it was diatomic gas, so it has degree of freedom 5, so 5 by 2, and number of moles n into R into T. The final kinetic energy is, there are two gases now. We have diatomic gas, we have monatomic gas. Okay, so for diatomic we have the n minus n moles present. For monatomic we have 2n moles present. So this can be written as 5 by 2. Okay, 5 by 2 n minus n RT plus, for atomic, monatomic, the degree of freedoms are 3. So 3 by 2, the number of moles here are 2n RT. So the total final kinetic energy can be written as, uh, let's do some calculation here. So this will give us 5. So let me take half 5n minus 5n plus 6n and then RT. Okay, so this will give us half into 5n plus small n into RT. Okay, so this is the final kinetic energy, this is the initial kinetic energy. Now the change in kinetic energy is final minus initial, which can be written as 5 by 2 nRT plus n by 2 nRT minus 5 by 2 n, sorry, capital N RT, and this will cancel. So final number is n by 2 RT. So half n RT is the change of kinetic energy. So option A is the right option. Okay. Now let's move to question number 3. In an ideal gas at temperature T, so the gas type is an ideal gas. It is at temperature T. The average force that a molecule, okay, so the force applied by a molecule on the walls of the closed container depend on T as it is given that the force on the walls of the container depends on T raised to power Q. A good estimate for Q is, okay. So we know the force, or we know the pressure on the wall of the container is 1 by 3 rho BRMS square. And if we want to calculate the force, then force is pressure into area. And because we have to calculate for one molecule, which we can assume it's a small area. So simply 1 by 3 rho A VRMS square, where RMS is the RMS speed of the gas molecules. Okay. Now we know that VRMS is directly proportional to root T. Okay. So therefore we can write from here that F, because density, area and 1 by 3 all are constant, so F is directly proportional to VRMS square, which in turn directly proportional to T. Okay. So, and in question it is given that F is directly proportional to T raised to power Q. Now simply comparing both of them, we can write Q is equal to 1. Okay. So C is the right option here. So let's move to the question number 4. Now it is given for a gas Cp minus Cv is equal to R. Cp minus Cv is equal to R in a state P. Okay. So the gas is in state P, where it follows Cp minus Cv is equal to R. And Cp minus Cv is equal to 1.1 R. So if this is true, then the gas state is Q. And Tp and Tq are the temperature in two different states. Okay, so Tp and Tq are the temperature of the gas in two different states. Okay, then we just need to comment on Tp and Tq, which one is larger and which one is smaller. So we know for an ideal gas, Cp minus Cv is equal to R. But for real gas, Cp minus Cv will not be equal to R. Maybe something like some constant into R, which is given here 1.1. So 1.1 R. So this means the first state, which is state P, is the state of the gas when it's behaving like an ideal gas. And Cp minus Cv is equal to 1.1 R is state Q of the same gas. This means in this state, this gas is behaving like a real gas. Now we know a real gas behaves like an ideal gas at real gas. It behaves like an ideal gas, okay, at high temperature and and maybe we can say and low pressure. Okay. So this means definitely the temperature at state P must be greater than temperature at state Q. That's why this gas is behaving like an ideal gas at in state P. Okay. So this means temperature at P must be greater than temperature in state Q. Since Tp is greater than Q, so option D is the right option. Let's move to the next one. Here, in question number 5, it is given that two ideal polyatomic gases at temperature T1 and T2. So these are two polyatomic gases. Don't know the state whether they are mono, di, or maybe triatomic gases, tri or more than that. So let's say these are polyatomic gases, and the at temperature T1 and T2. So both the gases, they are at temperature T1 and T2. They are mixed so that there is no loss of energy. Okay, so good part is that when we are mixing them or we mix them, there was no loss of energy. Okay, this means the internal energy of first gas plus internal energy of the second gas before mixing is same as of the internal energy of the or both the gases after mixing. Okay, so there is no loss of energy. Where F1 and F2 are and M1 and M2, N1 and N2 be the degrees of freedom, okay, masses and number of molecules of the first and second gas respectively. The temperature of the mixture of these two gases is, okay. Okay, let's write down. So let's now write down the internal energy of the first gas before mixing. It's simply the number of molecules multiplied by degree of freedom. Let me write capital F here. Sorry, F1 by 2 Boltzmann constant K into temperature T1, because we are dealing with the number of molecules here. So that's why we are writing Boltzmann constant. If it was a number of moles, we could have write gas constant. Okay, so just remember this thing. So V2 U2 is N2 into F2 by 2 KT2. Okay, now after mixing, the temperature of both the gases will be same. So and the number of molecules will be N1 plus N2. So we can write then for the first gas it will be N1 into F1 by 2 into K into T. Let's say the final temperature is T. Then for the second gas, N2 into F2 by 2 into K into T. Okay. Now it is given that there is no loss of energy. This means the total initial energy is equal to the total final energy. So therefore we can write N1 F1 by 2 KT1 plus N2, sorry, N2 F2 by 2 KT2 must be equal to N1 into F1 by 2 into KT plus N2 F2 into KT. Okay. Now K by 2, K by 2, K by 2 and K by 2 will cancel out. So this will become N1 F1 T1 plus N2 F2 T2, and this will become N1 F1 plus N2 F2 into T. Okay. Now the temperature of the mixture can be easily written down that N1 F1 T1 plus N2 F2 T2 divided by N1 F1 plus N2. Okay, so out of these given options, option B is the right option. Okay. Now let's move to question number 6. Here it is given that n moles of a perfect ideal gas, n moles of a perfect ideal gas undergoes a cyclic process ABCA. So there are n moles. and it is undergoing a cyclic process as shown in the figure. So it is from A to B, B to C, and C to A, and it's a PV diagram. So anyway, it is written though A to B is an isothermal expansion at temperature T. So here the temperature is constant, it's an isothermal process. So that the volume is doubled from B1 to B2. It's an expansion and volume is doubled. Okay. And pressure changes from P1 to P2. Okay. Now BC is the isobaric compression for, so BC is an isobaric process and AC is the isochoric process. Total work done in the complete cycle. Okay. So let's write down the work done for cycle A, B, C, A. And this will be equal to work done from A to B plus work done from B to C plus work done from C to A. Now because C to A is an isochoric process and we know the work done is PTV and it's an isochoric process CA, and so changing volume is zero, so delta V is zero. That's why work done for CA is zero here. Now there are only two things left: work done for an isochoric and work done for an isothermal process. Sorry, isobaric and isothermal process. So we know work done by an isothermal process is nRT, nRT natural log final volume divided by the work done by an isothermal process we know is nRT natural log of final volume divided by initial. Okay. Now this is given in this equation that work done then from A to B is N, N is the number of moles, R gas constant, T is the temperature, natural log. The final volume at B is 2 times of V1, so 2V1 by V1. So this will be, so work done by A to B can be written as nRT natural log of 2. Now work done by AB, it's an isobaric process. So this simply can be written as work done A to B is pressure constant and simple integration of dV. And because this is from state B to A, so V2 to V1. Okay. And this is, okay. Now this will become, okay, this will become pressure which is P2 into V2, V1 minus V2. So this will become P2 into this is uh, V1 minus V2. V1 is V1 and V2. V2 is twice of V1. Okay. This will become twice of V1. So this is V1 minus 2 times of V1. So this will become P1 V1. Okay. Now we know for an ideal gas that PV is equal to, sorry. Okay. Let me just clean this. I only put it P1. So this must be equal to P2 and V1. Okay. Okay. That's good. Now from A to B, we know that volume at A is P1, sorry, pressure at A is P1 and volume is V1. So P1 V1 and temperature at A is T. So and to B this must be equal to P2 B2. Okay, because temperature at A and B are equal. So P1 V1 must be equal to P2 B2. So P2 can be calculated in terms of P1. Okay. P1 then P2 is equal to P1 V1 by V2. So P2 is equal to P1 V1 by 2 times of V1. So P2 is P1 by 2. Okay. So this can be written as minus of half P1 V1. Now we know for ideal gas PV is equal to nRT. So this means P1 V1 is equal to nRT because temperature is same at both the places. So from A to B and that is T. So P1, so this work done from A to B can be written as minus half. In place of P1 V1 we can put nRT. So this will become minus half nRT. So total work done now from A to B is this, and sorry, this is not from A to B. This is the work done from B to C. Okay. Now total work done is work done from A to B plus work done from B to C. So nRT natural log 2 plus, which is minus of half nRT. So this will give us nRT natural log 2 minus half. Okay, that's the work done in this whole process. So option D is the right option. Okay, now let's move to question number 7. In this question, the initial pressure and volume of an ideal gas are P naught and V naught. So these are the initial, sorry. So the initial pressure and volume are P naught and V naught. The final pressure of the gas when the gas is suddenly compressed. Okay, let's make use of this word. Suddenly compressed to volume V naught by 4. The new volume is V naught by 4. Gamma is the ratio of specific heat at constant pressure and at constant volume. Okay. So we know gamma is Cp by Cv. Okay. Now because the gas is compressed suddenly, so this process will behave like an adiabatic process. Okay. Now because this process will behave like an adiabatic process, so we know in adiabatic process PV gamma is equal to constant. So we can write P naught V naught raised to power gamma must be equal to the final pressure multiplied by final volume V naught by 4 raised to power gamma. And from here we can write P is equal to 4 raised to power gamma P naught. Okay. Option number B is the right option. Okay. Now let's move to question number 8. Let gamma 1 be the ratio of molar specific heat at constant pressure and molar specific heat at constant volume of a monatomic gas. So gamma 1 is the ratio of specific heats for a monatomic gas. Okay. And gamma 2 be the similar ratio for the diatomic gas. Considering the diatomic gas molecule as a rigid rotator, the ratio, okay. So this means the diatomic gases we only need to consider translatory and rotational modes only, because that's what it is mentioning, that it's just the rigid rotator. Okay, so there is no need to assume the vibrational mode. Okay, now We need to find out the ratio gamma 1 over gamma 2 is. Okay. We know gamma 1 for a monatomic gas is 3 by 5, whereas for a diatomic gas, this is for mono, this is for diatomic, is is 5 by 7. Okay. Now we need to find out gamma 1 and gamma 2. So gamma 1 by gamma 2 is equal to 3 by 5 over 5 by 7, means 7 is on a 21 by 25. Okay. So here D is the right answer. Now let's move to next question. 1 mole of an ideal gas at 27 degrees C. So here is talking about there is N is equal to 1 and we have at 27 degrees C is taken from A to B. So okay. In the PV indicator diagram. So this diagram clearly shows that this is an isothermal process. And it's also mentioning that the temperature is 27 degrees C when it was taken from A to B. Okay, in the given PV diagram, the work done by the system will be, okay, okay. As we know, work done for an isothermal process is nRT natural log of V final over V initial. Now it is given that we know final volume, which is 4, initial volume, which is 2 here. So we can write N, and N is 1. R, the value is 8.3 joule per mole per Kelvin. So if it's in Kelvin, so we can easily convert 27 degree into Kelvin, which is 300 Kelvin. Natural log of 4 by 2. Okay. So this will give us 8.3 into 300 into natural log of 2, and this will become 8.3 into 300 into natural log of 2 is 0.6931. Okay, let me do a small calculation here. Okay, let me do a small calculation here. This is 8.3 multiplied by 300 multiplied by 0.6931. So this will give us 725. Okay, 0.8. Okay, this we need to mention into 10 raised to power. I think this is something. Yeah. 10 raised to power minus 9 joule. Okay, so for 10 raised to power minus 9 joule. Okay, so this must be equal to x into 10 raised to power minus 1 joule. Okay, we need to find out the value of x. So that will become 725.8 divided by 10 raised to power minus 1 is equal to x. Okay, so that will give us 258. Okay, it's into 17258. So that is, so value of x is 17258 into 10 raised to power minus 1. Let's move to the next question. This question says 1 mole of a monatomic gas is mixed with 3 moles of a diatomic gas. So for monatomic gas, sorry, for monatomic gas, the number of molecules are 1. Let's take it N1. And 3 moles of diatomic gas, let's say N2 is equal to 3 for diatomic. The molar specific heat of mixture at constant volume is alpha square by 4 into R, joule per mole per Kelvin. Then the value of alpha will be F by 2R. Okay, and mixture. Okay, so let's. Okay, CV of the mixture can be written as N1 CV1 specific heat at constant volume for first process plus N2 CV2 divided by N1 plus N2. Okay, and CV1 can be written as degree of freedom, and it is a monatomic gas, so degree of freedom are 3 F by 2 R. Okay, CV2 can be written as the degree of freedom for diatomic, which is 5 by 2R. So this we can write here, n is 1 into 3 by 2R plus, okay, 3 into plus 3 into 5 by 2R over 3. Sorry, no, 3, 1 plus 3, 4. Okay, now let's solve it. This will give us 5 3s are 15 and 15 plus 18. 18 by 2R into 4, and this will become 9. Okay, so 9R by 4. Okay, so this became 9R by 4. And this is given as alpha square by 4. So alpha square by 4 is given as 9R by, sorry, R by 4. So R and R cancel out, and 4 cancel out. So alpha is equal to 3. So we can write the value of alpha is 3. Okay. So with this, we conclude the session for kinetic theory of gases. Thank you. Thanks for your time. Okay. Yep.
क्लास बंद हो गया ना मैंने इसको बंद कर दूं मैं क्लास करता हूँ सर एक मिनट दो मैं करता हूँ सर